on page 280, and I'm not going to leave this up for you to copy all of this down right now because we're going to break down each of these steps in a specific example, but this is on page 280 for reference. And again, you will be doing this as a take-home test, so you can always reference this in your book or in your notes anytime you need to. And so a curve is basically just a word for a graph. And so if we are graphing a function, we can use what we have done so far in chapter 4 and this overall technique to get a good idea of what the graph looks like and sketch it without first looking at a graph on a graphing calculator. So we basically have 4 steps. We are going to analyze the function itself, f of x. We will analyze f prime, which was everything we were doing in section 4.1. We will analyze f double prime, which is what we were doing in 4.2. And then we will put all of that together. So we're going to go through an example of this graphing strategy. And so these graphing problems are basically like multiple problems in one, because we are going to be finding critical points and local maxima and minima and inflection points and all of those things that you've been finding in the first couple sections of this chapter. So all of these steps are going to be broken down on the following pages. So these are the instructions that would be on a homework problem for this kind of question. I'll give you a moment. Okay, so our instructions are to summarize the pertinent information obtained by applying the graphing strategy and sketch the graph of y equals f of x. So that means we're going to go through the graphing strategy that I was just showing on the previous page and find all of the important pieces of information from a graph. So this is our function. So this is a rational function. And our first step is to analyze f of x. So analyzing f of x is really not a calculus thing. This is sort of a throwback to college algebra or pre-calculus and some of the stuff we have done in we did in our review section of this class. So that means that we're going to find the domain of this function, find the intercepts of the function, and the asymptotes. We have worked with asymptotes in this class as well. So let's start with domain. What is the domain of this function?
All real numbers.
There's one number that doesn't work in the domain. So it's not quite all real.
0.
0, yes, exactly. 0 does not work in this function. So for looking at the domain, so this is a rational function. So if we have a denominator, we need to check to see if it's possible for that denominator to be 0. So we have to check the denominator. So for this denominator, we have x squared in the denominator, which means that x cannot equal 0. X can be anything other than 0. So if we're writing this in interval notation, it would be negative infinity to 0, union 0 to infinity. So we have our domain. We can't have a 0 in a denominator, so x cannot equal 0. Now we need the intercepts. This is going to be a little algebra review. So that means we need to find the y-intercept and x-intercepts. In general, for any function, how do we find a y-intercept?
Put it into decimals.
No.
This is going back.
What is the x value on the y-axis?
0.
0, exactly. So no matter what function we're looking at, it doesn't matter. To find the y-intercept, we always plug in 0 for x. That is true no matter what kind of graph we're working with. The y-intercept will always be when x is 0. So we're basically just finding f of 0.
It's going to be -8.
So let's plug it in. So our function,
So there isn't a y-intercept?
yes, exactly. So if we try to plug in 0 for x,
Oh, because the denominator is 0.
yeah, exactly. We have 0 in the denominator, which is undefined. So you don't really need to go through plugging in 0 in this case because we already found that 0 is not in the domain. So it's impossible to plug 0 into this function, but we always can do that just to check. But if 0 were in the domain, we would do the same thing, plug 0 in for x and find the y that goes with it. So that means there's no y-intercept. So we found the y-intercept, or found that it doesn't exist. So our next step, and I did not leave myself room here. We're not there yet. So now we need to find the x-intercepts. And I don't know just yet if there's more than one. So how do we find x-intercepts of a function?
Plug 0 in for y?
Exactly, plug 0 in for y. X-intercepts are where the function equals 0 or when y equals 0. So it's just the opposite. So we have our function. So we're setting just that whole function equal to 0. X. That was a plus. So we can actually make this equation simpler because we have a fraction is equal to 0. So we actually don't care about that denominator. In order for this whole function to equal 0, the numerator has to be 0. You can also think of that as cross multiplying. If we cross multiply this x squared over, the x squared just goes away. So really all we have is 0 equals x squared plus 2x minus 8. And if this is factorable, we can factor it to solve. If it's not factorable, then the quadratic formula or completing the square would be our options. But this is factorable. So our x-intercepts for this function are -4 and 2. So a rule of thumb for finding intercepts is that we plug in 0 for the other thing. Finding y-intercepts, we plug in 0 for x. Finding x-intercepts, we plug in 0 for y. So I'm going to scroll back up for a moment. So this first step of analyzing f of x, so we found the domain by checking to see what would make the denominator 0. We found the intercepts, at least those that exist. And now we need to find the asymptotes. So I'm just gonna, I really didn't leave myself room here. I'm gonna rewrite the function down here so we can look at it. Okay. So our function is f of x equals x squared plus 2x minus 8 over x squared. We already did everything we need to figure out what the vertical asymptote is. What is our vertical asymptote?
Would it be 0?
0, exactly. So that's where our function is undefined. That's that break in the domain. And this doesn't cancel at all. There's no canceling possible. So we know that's not just a hole. It's definitely an asymptote. So our vertical asymptote should come from what's not in the domain. And the horizontal asymptote would be in the form y equals. And what would that be?
1.
1, exactly. And how do we get 1?
Because it's x squared and then on the top and bottom, so you just divide the coefficients.
Exactly. Same degree on top and bottom, and so we're dividing those leading coefficients. So we did that earlier in this class as well.
Madeline, that's a V.
It's a what? Sorry. Do I have a typo?
No, I'm sorry, I lost connection for a second. It all came up. It's fine. Thank you.
Oh, okay, good. Okay, so we have our asymptotes. At this point in this class, I trust you to be able to find these vertical and horizontal asymptotes. So there's really no work to show here. So it's okay if you just write these as they are. So that is step 1, analyzing the function itself, finding the domain, finding all of the intercepts, and finding all the asymptotes. If this were just a regular polynomial, it might not have asymptotes, but if we have a rational function like this, it will. So we're going to go to step 2, and I'm actually going to make a new page because this is going to get long. So I'm just going to copy our step 2 over to a new page and come back and forth. All right, and I'm going to copy that function back over also. Oops. So this is the same problem. We're just continuing. So step 2 is to analyze f prime of x. So this is all of the stuff that we were doing in section 4.1. Figuring out what the first derivative of a function tells us about our graph. So that means finding partition numbers, finding critical numbers, finding intervals where the function is increasing and decreasing, and finding local extrema. So before we do any of that, we need to know what f prime actually is, because f prime will tell us how to get those things. There are 2 ways to find the derivative of f here. And I personally think one way is easier.
Product rule?
Well, okay, so there's more than one way. We technically could use the product rule, but we would have to bring that x squared up first and turn it to an x to the -2, which I also wouldn't recommend.
Okay.
We could use the quotient rule, since this is a quotient. But way back when we were first doing derivatives, first learning the power rule, we were actually able to do something to this function to make it possible to use just the power rule. Did I freeze?
No, you're good on my end.
Oh, okay, great. My video froze on my end for a second. Okay, so we can actually do something to this to make it possible to use just the power rule. And that is, since we only have one term in the denominator, you can actually separate this into 3 parts. And we can simplify each of those and apply the power rule to each. So this is all still just f. There's no derivative just yet. So x squared over x squared is just 1. 2x over x squared is 2 over x. And nothing cancels in the last one. So to use the power rule here, we need everything in the form of x to a power, which means those x's would have to move up. So this is all just using algebra rules to change f a little bit so that we can use the power rule to take this derivative. So using the power rule, that 1 goes away. 2x to the negative 1 is now negative 2x to the negative 2. Minus 8x to the negative 2 is now plus 16x to the negative 3.
And you can only separate those because they're addition, correct?
Yes.
Okay.
And because there's only one term in the denominator. So we can just divide everything by that one term.
Okay.
So I personally like this method because we can avoid the quotient rule, which I just prefer. But the trouble with this method is that now that we've taken the derivative, in order to use the derivative, we need to get it back into a form like the function started. So we would have to go back to having x in the denominator and putting it back into a rational function. So now that we've done the derivative, this is now negative 2 over x squared plus 16 over x cubed. And anticipating what we're going to do with this derivative, solving it with it equal to 0, we want to get these two terms together, which means we need a common denominator. So if we have x squared and x cubed, our common denominator is x cubed. So we would have to multiply each of these by x. So we have to be comfortable with power rules, changing positive and negative and things like that, and with adding rational functions like this, getting both of these rational functions with the same denominator, which is x cubed in this case. So now we have f prime. So finding f prime is like a little problem in itself, but we haven't actually found any of the things we need in step 2 yet. So step 2, we're trying to find partition numbers, critical numbers, and intervals where the function is increasing and decreasing, and local extrema. So starting with partition numbers. And I'm specifically saying partition numbers of f prime because partition numbers can be found for any function, and we will find them for f double prime in the next step as well. So what are partition numbers? What are we trying to find when we're trying to find partition numbers?
Where f prime changes signs.
Not necessarily. It is often the case, but not always. So partition numbers of f prime are where f prime equals 0, or f prime is undefined. So anytime we're finding partition numbers of anything, it's when that thing is either 0 or undefined.
So it would be 0 because you can't have 0 on the denominator, correct?
Right, exactly. So if we have f prime is undefined, we would set the denominator equal to 0. Exactly. So set the bottom equal to 0. So the denominator is x cubed, which means x equals 0. So that's one of our partition numbers because that's a number that makes f prime undefined. If we want to know where f prime equals 0, I'm just going to write all of f prime for a moment so we can look at it. For a fraction to equal 0, the numerator has to be 0. So that denominator doesn't actually matter for this problem. We just need to know where the numerator equals 0. So to find where f prime equals 0, we'll set the top equal to 0. Yes.
Oh, wait. 8.
So 8, yes. So on your homework, there were some where the numerator was just a number, in which case it's not possible to solve that because we can't have a number equal to 0. But if we do have stuff in that numerator, we need to set the top to 0 and solve. So we have two partition numbers here. x equals 0 and x equals 8.
Can you write them together like x equals 0, comma 8? Or do you,
Yes, that's fine.
okay.
I just want to highlight them for now so we can look at them separately for critical numbers, but it's fine if you just write x equals 0, comma 8.
Okay.
So there's a confusion. I got a handful of questions about the difference between partition numbers and critical numbers. Partition numbers are any numbers that make the derivative either 0 or undefined. So that's what we found here. Critical numbers, which is the next thing we're supposed to find for this problem, critical numbers always come from the partition numbers. So we'll never have any critical numbers that are not there. So we've already done all of the work to find the critical numbers. But the thing about the critical numbers is that they must be in the domain of F. So to find the critical numbers, we have to look back at our partition numbers and think which of these is actually in the domain of our function. So what are our critical numbers or number?
Zero.
Is 0 in the domain of our function?
Maybe I don't understand what that means.
It should be,
So, what was that?
it should be 8.
8, yes, exactly. So let's go back to step 1. So in step 1, we were analyzing f of x, and the very first thing we did was to find the domain of f. And the domain of f was everything except 0.
Okay, so it can't be 0 because it's everything but that number.
Exactly.
Okay.
So since 0 is not in our domain of the original function,
Okay.
it is not a critical number.
So it is based off of the function of x, not the derivative of x,
Right, yes.
which I don't know if that'd make a difference, but
It does, because they don't always have the same domain stuff. So
okay.
yeah, it's always based on the original function. So x equals 0 is not in the original, or is not in the domain. Ah, what did I just do? Okay. So we found partition numbers, which includes everything that makes the derivative either 0 or undefined. And then we found the critical numbers, which are the partition numbers that are also in the domain of F. Okay, so we're still on step 2, analyzing the first derivative. And this, just a little side note on your homework, this, what we've done so far in step 2, were like some of the problems, 27 through 30, I believe, where you're finding the first derivative, then finding the partition numbers, and then finding the critical numbers. But now we're going to take that further and use those pieces of information. So we found partition numbers and critical numbers. So now we need to know where this function is increasing and decreasing. So this is where we make a sign chart of f prime. Using all of the partition numbers. So partition literally means like to separate things into, I don't know, separate things. So partition numbers are giving us ways to partition the number line. That's why they're called that. So we will have our number line.
I'm sorry, Madeline. Is this still part of step 2?
Yep, it is. So step 2 has, well, all of the steps have lots of steps to them. So step 2 is all of the stuff we can do with the first derivative. And so our partition numbers were 0 and 8. And above those partition numbers, we can say what's going on with the derivative. So the derivative is not defined at 0. And it's 0, it's 0 at 8. That's how we found those partition numbers. So this is where we find out
What makes 8 0?
because
Is that the critical number?
not because it's a critical number, it was because when we found 8, it was from setting the first derivative equal to 0.
Oh, okay. Okay.
And 0 came from f prime being undefined.
Thank you.
Mhm. So our sign chart is really just plugging and chugging. We're going to plug this, take a test number from each of these sections and plug it into f prime to see whether it's positive or negative. So
Negative 0.1 and 10.
I like those ideas. So we can't use 0 here because 0 is one of our partition numbers, but other easy numbers, -1, 1, and 10. So we're plugging those all into the first derivative, which was -2x plus 16 over x cubed. And I'm just going to write that right here so it's handy. And you can just plug these into a calculator if you prefer. You don't have to do that by hand. So on top we have positive 18 and on the bottom we have -1. So that is definitely a negative number, a negative 18. So we have negatives up to here. So then when we plug in 1, we have 14 over 1, which is a positive number. And 10. So that's negative 4 over 1,000, which is negative again. So on what interval or intervals is the function increasing?
0 to 8.
0 to 8 exactly. Oops, that's not an 8. It's sideways 8. So anywhere where our derivative is positive, we have an increasing function. So that means it's decreasing everywhere else. So from negative infinity up to 0, and from 8 to infinity.
To infinity.
So now we know where our function is increasing and decreasing. So our first derivative gave us partition numbers to divide up this line. It gave us our critical numbers, which is 8. And it gave us increasing and decreasing. There's one more thing that is in step 2 for analyzing the first derivative. So we've done that. And so the last thing is the local extrema. So that means local min and or max. So looking at this sign chart, we can actually tell where we have a local extrema. And I'm just gonna write it again. You don't have to write it again, but I want to be able to make some notes. Oops. So we had 0, which is not defined. We had 8, 0. So where, what do you think? Where would we have a local minimum or a maximum?
Would the maximum be at 8?
Yes, exactly. So that's because our function is increasing up until 8, and then it's 0 at 8, and then it starts going down. So we can just sort of imagine what's happening around that number based on the increasing and decreasing. It's going up, it reaches 0, and then it goes down. Do we have any other local extrema?
Wouldn't there be one at 0 also?
Would there?
It's an asymptote, isn't it?
Yes, exactly. We know from our very first step, well, the first step, analyzing the function, that there's an asymptote here.
So does that mean there's no local minimum?
Yes. And even if we didn't recognize it as an asymptote necessarily, just the fact that it's not defined there means that there can't be a local minimum or maximum because there's no function at all at 0. The function is just not at 0. So we don't have a minimum or maximum there. Local extrema are always at critical numbers. Oops. So local extrema have to be in the domain of F, otherwise there's no way for them to be a maximum or a minimum because they wouldn't exist if they weren't in the domain. So local extrema are always at critical numbers. So there's only a local maximum here. So we have a local max at x equals 8. But our actual maximum is the function value at 8. So we would need to plug 8 into our function, which was x squared plus 2x minus 8 over x squared. Not 9. That's not right. 9 over 8, that's what it is. So all of those steps of step 2 of analyzing the first derivative are building on each other. So that's all of step 2. So we have used everything that we did in section 4.1 to find out all we can about the function from the first derivative. So our next step, step 3, is going to be about the second derivative. Are there any questions about this first derivative stuff before we go on to step 3? Was that a question?
Sorry, I keep getting cut off. No, Ringo.
Was there a question or are we
Can you
ready?
hear me now?
Yes.
No, I did have a question. Sorry, I keep getting kicked off and reconnected. So that equation that we're pulling from, that is the original equation, correct?
Yes.
Okay. Is there a time that we pull in the derivative?
Only when we are using it to make the sign chart.
Okay. Oh, okay. All right, that's good to know. Thank you.
But the local max is an actual point on the actual function, so that's why we plug it into the original function, because we want to know the actual place that it lands on the graph. Okay, so I'm going to come copy step 3. And make a new page. And I'm just going to copy our function as well. Okay. So step 3 is analyzing f double prime, the second derivative. So all of step 3 is what we did in section 4.2. So again, we're going to find the partition numbers of f double prime this time. We'll find where the function is concave up and down, and we'll find any inflection points. So to do these things, we first need to find f double prime. So we need f prime. So we can use that same technique as we did for finding the first derivative, which is to separate it into parts and use the power rule, and then put it back into a rational function. The other option is to use the quotient rule, and we can use either of those for either of these problems.
Can we do the quotient rule?
Yes, that sounds good.
Positive. Thank you.
So if we use the quotient rule, we have our top, which is negative 2x plus 16. So remember, we're doing the second derivative now, so we're starting with the first derivative. And our bottom is x cubed. So t prime is just negative 2, and b prime is 3x squared. Got a t here. So our quotient rule is b t prime minus t b prime all over b squared. So now we're going to get f double prime by putting all of this into the quotient rule. So bottom is x cubed times the derivative of the top minus 2 minus the top negative 2x plus 16 times the derivative of the bottom 3x squared all over the bottom squared. So on the top, that first little bit is just negative 2x cubed. We need to be super careful on the top there. So I'm going to do this in 2 steps. So if we leave that minus sign out there and we distribute that 3x squared in, we would have negative 6x to the 4th plus 48x squared. And on the bottom, we end up with x to the 6th. And then we need to distribute that negative into the bottom. Oh yeah, I did make a mistake. I was wondering what went wrong. This should not be a 4. That should just be a cube, because that came from the 3x squared times negative 2x. Okay, so distributing that negative sign in, we now have 2x cubed plus 6x cubed plus 48x squared over x to the 6th. And on the top, we have like terms to combine, so we have 4x cubed plus 48x. Oops.
Is it supposed to be a negative 48x?
Yes, it is. After I was making such a big deal about being careful to distribute the negative. Thank you. So we have 4x cubed minus 48x squared all over x to the 6th. So this is just the quotient rule of plugging all of the t prime, and b prime into our quotient rule. But there's one last thing that we need to do here. Yes, it should. Thank you. So 2 things to do. One is to fix my typos. We should reduce this. In all 3 of these terms, there is an x squared that's common. So we can cancel an x squared out of everything. And it might be helpful to think of it as factoring out the x squared from the top. And then we can cancel x squared and x to the 6th. So that will be x to the 4th. That's one, for me, that's one downfall of using the quotient rule, is that we're likely going to have that last reducing step on a problem like this. And it's fine. And it won't really hurt anything. You should get the same answers for the partition numbers, even if you don't reduce, but it will make solving those equations to find partition numbers a lot easier if we do. So on this one, finding f double prime, we use the quotient rule. On finding f prime, we separated it into pieces and used the power rule and then put it back together. Either of those methods would have worked on either of these derivatives. So it's really a preference. Okay, awesome. So we haven't actually done anything with the second derivative yet, though. So our next step is to find the partition numbers, which is the exact same thing as we were doing with the first derivative. So these are, we're going to be finding the partition numbers of f double prime this time, which is the same thing. So these are the numbers where f double prime equals 0, or f double prime is undefined.
Undefined at 0.
Yes, exactly, undefined at 0. So for undefined, we will set the denominator equal to 0. Which means x to the 4th equals 0, which is just 0. And for f double prime equals 0, we'll just set the top equal to 0. Which is 4x minus 20.
12.
It's 12, exactly. So that's just like we did for the first derivative, and we now have partition numbers for f double prime. Whew. So what we do with these is very similar to what we did with our partition numbers of f prime.
Excuse me, Madeline.
Yes.
So no matter what derivative we take from the original equation, the domain remains the same, correct?
Yes.
Okay, very cool.
Yeah, so anytime we're talking about the domain, it's always going to be the domain of the original function, which is the very first thing we find in this graphing procedure. So for step 3, we have found the partition numbers. So next we need to find the intervals where the function is concave up and concave down. Which means we make a sign chart again. But this time we're making a sign chart for F double prime. And I'm just going to write F double prime here. So it is handy. And it was 4x minus 48 over x to the fourth. And so those partition numbers, again, are what partition our number line. So again, F double prime is not defined at 0.
0 at 12.
0, 12, exactly. And so
And
we're
negative 1. Sorry, negative 1, 1, and I guess 13. No number above 12 is going to be nice.
yeah, that's true. That sounds good. Negative 1, 1, and 13. So F double prime of negative 1. Is negative 52 over 1, which is negative 52. So on the bottom, I'm just leaving it as 13 to the fourth because that's definitely going to be a positive number. So it really doesn't matter what 13 to the fourth actually is. All we care about is that this is a positive over a positive, which makes it definitely positive. So if you want to put it into the calculator and get what that actually equals to, that's fine. But all we really care about is the sign, and that's enough information. Oops. So this sign chart gave us enough information to figure out where our function is concave up and concave down. So where is it concave up?
12 to infinity.
Yes, exactly. 12 to infinity. Positive second derivative means it's concave up. Where is it concave down?
Negative infinity to 12.
Almost.
Not including 0.
Yes, exactly.
Oh,
Can't
that's right.
include 0. You can use a union or a comma.
And then 0 to 12.
Right. So if 0 were in our domain, we could include it. But since 0 is not in the domain, we have to skip it. So that's kind of a tricky part that we have to pay attention to.
Yes.
We're so close to having all of our information to graph. So the last thing that the second derivative tells us is inflection points. So I'm just gonna rewrite that sign chart. You don't have to. So we have 0, 12, negative, negative, negative. Okay, where do we have an inflection point?
At 12?
At 12, yes. How can we tell?
I'm a good guesser.
It is a good guess.
It's where the signs change.
Exactly, yes. So an inflection point is where the concavity changes from down to up or up to down, which on our sign chart means the sign changes positive to negative or negative to positive. So this is an inflection point.
Now, if that 0 was not defined, if it was defined, then would there be an inflection point at both points?
If, no, because the sign is not changing there, so it wouldn't be an inflection point either way.
Ah, okay.
But if we like pretend for a second that this was plus, as long as that number is in the domain of the original function, it's an inflection point if it's changing signs.
Okay.
But an inflection point is the whole point, and so we need to plug the 12 back into our original function to find what the y value is for that 12. So back to the original f, which was x squared plus 2x minus 8 over x squared. It is. Let's write it down.
Can you just cross those? Oh, no, never mind.
Ah.
Is there a reason why you use the coordinates for this point, for the inflection point, but we use the function notation for the local max?
Yes, it's mostly style, so really it's not a huge deal if we switch, but the reason is that the inflection point is the whole point. It's the X and Y values. Whereas technically the local extrema, local min or max, the actual local maximum is the 9/8 part. It's the maximum that's actually achieved. And so the focus is on that, but writing it in function notation is just a way of saying the local max is 9/8, but it happens when X is 8.
Makes sense.
Yeah, it's mostly kind of style, but so we have found all of the information, which is great. So I'm going to go back to the original instructions for a moment. We were asked to summarize the pertinent information. That means all of that stuff that we just found. Domain, intercepts, asymptotes, partition numbers, critical numbers, increasing and decreasing, concavity, and the inflection points, and local extrema. All of those things are the summarized pertinent information part. Our next part is to use all of that to actually graph this function. And so I'm again gonna copy and paste our step 4. I don't know why this is so hard right now. All right, so our step 4 is to sketch the graph, including all information from the previous step. So everything we just found should be a part of our graph. And so this is easier when you're sort of working on a piece of paper or in a notebook because you can kind of flip back and forth, but I'm just going to write all of our information that we just found. So we just found that the domain is everything other than 0. We found there's no y-intercept, but the x-intercepts are at 4 and 2, or was it negative? Where did you go? Negative 4 and 2. And we have a vertical asymptote at
0.
0, thank you. And a horizontal asymptote
1.
so y equals 1. So that was all of our step 1 information. In step 2, we found the critical number was x equals 8. And what really we need to know about that critical number is that we had a local max, not mix, at f of 8 equals, what was that? I just had it, 10/9. No, I'm looking at the wrong thing. 9/8 was our max, right? Yeah. And so before even writing increasing and decreasing, I'm just going to finish writing the sort of important points that we found. So we found local max was an important point, and we found the inflection point. was 12, and this one was the 10/9. So before even going to the increasing, decreasing, and concavity parts, we can put all of this stuff on our graph. So asymptotes are usually a good thing to start with. So we have a vertical asymptote at 0. And we have a horizontal asymptote at 1. And just planning ahead so that this graph is easier to read, our maximum is only 9/8, which is just barely over 1. So I'm going to sort of make a decision to change the scale on this graph to be two lines for every unit in the y direction. In the x direction, I'm just going to keep 1. So I'm sort of adjusting the scale, etc. So our horizontal asymptote is at 1. Then we also have the important points of the x-intercepts. Oops, how did that happen? The x-intercepts are at -4 and 2. And we know we have a local maximum at 8, 9/8. So 8, 9/8 is just barely over 1. And we also have an inflection point, and I'm just going to extend this a little bit. 12, 10/9. So we have all of these points on the graph that are helpful, and we have our asymptotes. But to fill in really what the shape of the graph should look like, we can use our increasing, decreasing, and concavity, which I am going to write sort of below the graph here. So our graph was only increasing from 0 to 8. That's what we found in step 2. And it was decreasing everywhere else. So it's decreasing along here. And then we also have our concavity. So our function was concave down. From -infinity to 0. It was also concave down from 0 to 12. And it was concave up from 12 on. So those pieces of information tell us our shape of our graph. So before even putting it on the graph, last week we talked about those 4 shapes that come from the combinations of increasing and decreasing and concavity. So decreasing and concave down looks something like this. Increasing and concave down looks like something like this. Decreasing and concave down again looks like this. And decreasing and concave up looks like this. So those four shapes of graphs are what our whole graph is made out of. So we use the asymptotes, the points that we have drawn so far, and those increasing and concavities to show us what our graph should look like. So this one, we know that since it has an asymptote, the graph should be getting close to the asymptote as it goes there. It's going to go through the x-axis at our x-intercept, and it's going towards the vertical asymptote. So that whole piece is decreasing, and it's concave down. So that whole thing is that shape. Our next piece is increasing and concave down, which means it should be going up, but that curve part is going down, and it's reaching its maximum at that point. So we have to remember that this is a max, even if it's a super slight max. Now it's decreasing because it reached its max, so it's going to start going down, but it's concave down. And it's just going to barely decrease to that inflection point. So it looks kind of flat, but it really did just barely hit a maximum right there. And now it's changing concavity here, even though it's going to be really slight because the graph is so squished. It's now changing to concave up and decreasing, which means that that end is sort of dipping out to the side. So using all of that stuff from the graphing procedure, we can get a graph of what this function looks like.
How come it crosses the horizontal asymptote?
So that's a good question. It comes up a lot. Horizontal asymptotes only do their asymptote thing when x is getting really big. A function can actually cross a horizontal asymptote when it's close to the center as many times as it wants to. It's just when it goes farther out, it's the limit as x goes to infinity or negative infinity that it can't. So horizontal asymptotes are different from vertical asymptotes. They actually can be crossed, just not as they go forever.
So eventually will that go back below that horizontal asymptote because it's decreasing?
It won't.
Oh, it won't. Okay.
Because it is decreasing forever, but it's decreasing in a very slight way where it's just getting closer and closer and closer to the horizontal asymptote.
Okay.
And so I want to bring this graph up on Desmos also so that we can kind of zoom into that weird max inflection point area because it is hard to draw nicely. And so let me switch things here a little bit. That doesn't work. Okay, so we have so here's our function. I'm going to zoom out to start with. So we can see that there is that vertical asymptote at 0, which we knew about. And we can see that there is a horizontal asymptote, which if we zoomed in, and I'm going to change this so it shows us every number. If we zoom in, we can see that horizontal asymptote is at 1. On the left side, it's getting closer and closer to 1. On the right side, it is crossing 1 for a second, but then it's going off, getting closer and closer to 1 on the right side. So if we zoom in a lot in this area over here, we can see we know that our local max was achieved at 8. And so if I hover over, we have 8, comma 1.125, which is 9/8. That's 1 and 1/8. And even though it's really hard to tell on this graph because the max is so slight, if we go a tiny bit to the right, oh, I can't. If we go, there we go. If we go a tiny bit to the right, the y value does decrease eventually. There we go. Once the digits catch up. And if we go to the left, the y value does decrease as well. So that really is a max, even though it's just barely achieving that maximum. And 12 is where our inflection point was. That is the 1.11 repeating, which is 10/9, 1 and 1/9. And the concavity is changing here. It's going from slightly concave down, curved downward, to slightly concave up, curved upward. I'm gonna see if I can sort of zoom in around that inflection point to show it more clearly. So it's starting to show a little more, but if we look at 12, we can see on this side to the left of 12, we do have a little bit of a hump there, whereas at 12, it's starting to flatten out a little bit. You can try to make it a little bit more. Can see it a little bit better here. So we can see our maximum being achieved there at 8. And we can see just barely at our inflection point here, there is a concave down curve here. And then as we go out, it's starting to be concave up. So the difference is super slight, but those inflection point and maxima, or the inflection point and local maximum that we found are achieved, even if they're subtle. All of this is why the chapter 4 test is a take-home test, because this is a lot to do. So there will be one graphing problem like this on your chapter 4 test for the take-home that will be a similar type of problem, this kind of rational expression where we have some weird types of things going on.
That's a lot in that problem.
Yes, it is lots of sub-problems. So again, this is the graphing strategy. This is in the book on page 280. And so I mentioned at the very beginning that I'm sort of jumping a little bit in the section. So in section 4.2, there's a more basic graphing strategy that only works for polynomials. And really the only difference is that it doesn't include asymptotes. So in general, we can use this curve sketching technique because it includes all of the possibilities. But if we were doing this for just a polynomial, of course, there wouldn't be asymptotes. And our domain is just all real numbers in that case. So we don't have time to add on to this today, but really all of this stuff we did was sort of a summary of everything we did in sections 4.1 and 4.2 and putting it all together. So there really weren't new things today. It was just like everything combined into one thing and then applying it to graphing. So it is a lot of stuff. And for your homework for this section, there will not be very many problems because there are so many parts to them as well. So on Thursday, we're gonna go back to 4.2 a little bit because there's one application that's in that section that we are going to do. And then we'll go on to 4.3 and probably 4.6 as well. So we don't have time to start another thing today, so that will be all unless there are questions. You are free to go and I'll see you on Thursday.
Thank you, Madeline. Have a good day.
You too. Oh, and there was no in-class activity. Just, yeah, I sort of spaced
Thank
that.
you.
So thank you for asking.
All right, have a good one.
You too.
You have a good day, Madeline. Thank you.
You too. Thank you. Thanks for bringing your dog today.
Oh yeah, he's new. He's a Great Dane. He's
Oh,
a little excited to hear people.
yeah, I always like seeing pets.
You have a good day.
You too.
Hey Madeline, so I had a few questions on the homework and I was just wondering if you would like me to go to the office hours to ask about those.
You can ask now since we have a few extra minutes, but then if it takes some time, we can switch to office hours.
Alrighty. So for problem 23 on page 249 for the homework.
Okay. Sorry, what number did you say?
23.
Okay. Yes.
I couldn't figure out, I looked in the back of the book and it said that it was F, but I can't figure out why, because I thought that it had a defined point at 5.
So let me look. So this one, I am drawing a very rough version of that graph. So this one, it shows 6 over here. And so it looks like that point is at 3 on the graph.
Mm-hmm.
Oh, and yeah, and it's going up to 5. I see what you mean. Sorry. I'm just catching up. So that is a defined point. However, the sign charts that you're choosing from are all about the first derivative. And so this function is defined all the way up here. It reaches a maximum at 3, 5. Its maximum is 5, and then it goes down. But the actual derivative is increasing, or excuse me, the derivative is positive here because the function is increasing.
Mm-hmm.
And the derivative is negative over here because the function is decreasing.
Right.
The tricky thing is that there is no derivative at this point up here.
Okay.
And that's because, oops. Basically, if we think of a derivative as like the slope of the tangent line and we try to draw a tangent line here, there's no good place to draw it because it's like this little point where we can't actually find a tangent. Whereas if we were doing a tangent down here, we could find it just barely touching. So anytime we have a point like that,
Mm-hmm.
the derivative is not defined.
All right.
So
But then,
that's why, yeah, that's why it says not defined there. Or actually, I think it has a little hole on the sign chart.
got it. But it would still have a local maximum of 5, correct?
Yes, exactly.
And my other question was off the, I can't say it, the partition numbers
Mhm.
for the next like section of the homework. I was looking at my notes and for the most part, I feel like I can find the critical numbers, but I can't find the partition numbers.
So if you are finding the critical numbers, then you have to be finding the partition numbers too, because critical numbers actually come from the partition numbers.
Okay.
So are you looking at like 27 through 30 on the next page?
Yeah.
Okay, so was there a particular one or just?
Like just in general, I tried problem 27 and I found the derivative, which was f prime of x equals 3x squared minus 12.
Yes.
And then
Okay.
I substituted 0 for it to
Mhm.
find the critical numbers. And then I got x equals -2 and +2.
So when you set that equal to 0, oops, that's not me. That doesn't make sense. That should be an x. Yes, so we do get x equals ±2 for that, so that's great. Those are actually the partition numbers.
Okay.
And so when we find where the derivative is 0 or undefined, which in this case, there's nothing that makes it undefined, those are first the partition numbers. Then the critical numbers are any partition numbers that are also in the domain of the original function.
Right.
So our original function was this. So what is the domain of that function? I'm going to ask it in a different way. Are there any numbers that we can't put in that function because it would make something undefined?
No.
Right, exactly. So the domain is actually all real numbers because there's nothing that can't go in that function. There's no denominator, there's no square roots. Everything is safe. Everything just is safe to plug in.
Okay.
So the critical numbers are, in this case, those same numbers because these are, the partition numbers are in the domain.
Okay.
So when you set the derivative to 0 and solve it, or when you find where the derivative is not defined, those are actually partition numbers first. And then we have to check to see, are those in the domain? And if they are, then they're also critical numbers.
Okay. Alrighty. Well, that answers my questions.
Awesome.
Thank you.
You're welcome.